Recording in progress.
So let's talk about how to handle number 6, okay? Now, I will be honest, this took me a few times to figure out. And I was going about the wrong way. You do not want to use conjugates. Don't. Nope. A conjugate is good to use if you see like the same kind of radical. If you see like a, like, or if you see square roots, because square roots kind of lend itself well for conjugates. But I would not do that here. Here's what you want to do. Think of it like this. Difference of cubes. Guys, let's focus, please. Thank you. Difference of cubes over difference of squares. You'll see. You'll find out. So here's what you do. Change this to this. Do 1 plus h. And yeah, if you didn't get the homework done, don't worry about it because I know I messed up the way I posted it. So if you want to work on it later in class or just turn it in next week, that's totally fine. Don't worry. That's why I'm not assigning any homework after today's class. Charlie, go.
I've just been going off through the stuff you post online. I don't think I ever got the homework taken out.
Oh, geez. I'll take care right now.
Oh, well, actually, I don't know. The 2-6.
And actually, I think what I meant to say was this is reversed. Yeah, that's what we're doing. So what I did was I converted the cube root to the 2/6 power. I converted the square to the 3/6 power. By doing that, then I could rewrite it like this.
Sorry, what did you do?
I converted cube root to 2/6 power because cube root is 1/3 power.
Oh, I see what you're saying. Okay.
So what I'm doing is I'm trying to find the common denominator for the exponents. That's what I'm trying to do. So now I can rewrite like this. I could say 1 plus h to the 1/6 minus 1.
Why wouldn't that be in the denominator? Because it's 2-6 minus 3-6. Oh, and then it's negative in the denominator.
Right.
That goes up.
Right. Yeah, I know. There we go.
What just
Okay.
happened? Oh, are you just multiplying by the conjugate now?
Yeah, you'll see what's happening. Here we go. I'm not doing any conjugates actually.
How did you wait? So how'd you get this?
I'm just running spam stuff right now.
It kind of looks like it. I'm not gonna lie.
I get that a lot.
Okay, are you gonna explain it once you're done?
No.
Okay.
Here we go. No, let me explain. Here's what's happening. Okay, I know it's a little crazy what I just wrote. Think about it like this.
That's the difference of
We
square.
have a squared minus b squared. We know it's this, right? That's easy. If you have a squared minus b, sorry, a cubed minus b cubed, hopefully you guys remember, not gonna have to talk
You never
about
taught us
that.
this.
No, just I don't think it's in the CPM. That's probably why you didn't.
A squared plus b squared plus ab.
Okay, so that's difference of cubes. Okay, now how am I applying it to this? If you think about it, your a is kind of like 1 minus h raised to the 1/6 power. Your b is kind of like 1, right? So if I were to square this, that becomes 1 minus h to the 2/6, that becomes 1 squared. Likewise here, right? My a is like 1 minus h raised to the 1/6 power. My b is like 1. So replace the a here with 1 minus h to the 1/6, replace b with 1. That's why I have 1 minus h raised to the 1/6 minus 1. And that becomes 1 minus h to the 2/6. Of course, ab, which is that times 1. And of course, 1 squared is 1. So what I've done is I deliberately changed this. This basically became a squared minus b squared. And this became a cube minus b cubed. That's what happened.
Oh, so one is the V.
So this right here
That's the third.
is like a. This right here is like b. A minus b. This right here is like a. This right here is like b. That is like a. That is like b. That is like a squared. That's like ab. And that's like b squared. That's what's happening.
I understand now.
Is this right here?
Yeah.
Because anything times one is itself. That's a, that's b. That's why. So now, what crosses off, guys?
1 plus h to 1 6.
That crosses off. Plug in 0, you should get 1 plus 1 over 1 plus 1 plus 1. 2/3. We're good. That we are answering. That's how we do it. That's why it's 2/3. Ron, yes, go ahead, Ron. I'll do 5 in a moment. Yes, yes. So 10 is pretty similar. 10, you can treat it in much the same way. Yeah, and that was a tough one. That was not easy. For 10, I'll do it down here. It's pretty similar. You x 1/3 minus 3. X 2/3 plus 3 x 2/3. So x 1/3, sorry, plus 9 all over. Okay. So you see what I did for number 10, and this is pretty similar, right? Yes, it's not x cubed, x minus 27, but if you think about it, x is the cube of x 1/3,
Third,
right?
and that's 30.
X minus 27 is no different than saying x to the 1/3 to the 3 minus 3 to the 3. You have to get creative that way. Those are the same thing. That's totally the same thing. So now you have your A, you have your B, and you have the formula for a cubed minus b cubed, and you do it. That's what we gotta do. And then these cancel. Then plug in 27, you should get 9. Do it correctly. Sorry, 27. The answer is 27. You get 9 plus 9 plus 9. Right.
Yeah.
You get 27. Right. All right. So those are pretty intense ones, 6 and 10.
I like as hard as it gets, or does it get worse?
For this, yeah, there's some that could go a little harder. But in terms of algebra, this is the hardest algebra gets. Yes, yes. There's other ones that can be a little more advanced. Now, for 5, that one you have to kind of think about graphically, I think, or numerically would be the best way to do this one.
Number 10.
Number 5.
Do you have an answer key for this?
I do not actually. Actually, I would do this.
Graphically, is that what you said?
Yeah,
Why?
I think.
I-
Well, if you're approaching pi over 2 from the left side of cosine x, that's getting pretty close to 0. And the top's also getting pretty close.
No, you can just multiply by the conjugate right there.
What's
And you get
conjugate?
1 minus 1 plus sine squared x.
Top, bottom?
Wait, why
Hold on.
Or sorry, 1 plus sine x.
Oh, I see what you're saying. So you're saying we should do this.
Mm-hmm.
That's cosine.
And then just cosine squared x. Like cosine.
But then you get 0.
Uh-huh.
Right?
Oh, yeah. Is that
Yeah.
the wrong answer?
No, I think it's right.
Yeah.
Yeah.
Minus sine or cosine x.
Does that make sense, Rohan? Yeah, and then you get cosine squared x up top.
Right.
That cancels.
Yep. And then cosine.
Yeah, if you plug in pi over 2,
Yeah.
you get 0. Yeah. Okay. Okay. Yep. I agree. I agree. Okay, let's actually go through the lesson now. All right. So do we leave it off with example 6? Hey, do we leave off example 6? What was the last one?
5B.
Okay, so let's go here. Okay, so guys, I want to finish off the notes. And then once I finish, we're done. I won't sign any homework over the weekend. And if you didn't get the homework done, just do it sometime this weekend. All right, so let's write this as a piecewise function. Guys, quiet, please. Thank you. All right. So to write as a piecewise function, I'm going to do this. F of x is going to equal. That's terrible braces. Let's see if I can do. Oh, you got me. Thanks. Sorry about that.
You want this up or should I just raise it up?
Raise it all.
Oh, there's only 1/4.
Oh, man. So basically to break out of the absolute, everything you just. Oh, yeah.
Okay. So what you do when you rewrite something, just so we get kind of the habit in those the patterns, right? Pattern recognition. If you have to rewrite absolute value, well, so first we'll back up a little bit. If you have to do a limit of an absolute value, best to rewrite that as piecewise. How do you rewrite that as piecewise? Take it as it looks and assume that x is bigger than that number. Because if x is bigger than -2, then x plus 2 stays positive regardless, right? So just keep it as is. But if you choose a value less than -2 for x, which clearly makes that expression negative, in order to still maintain the same positive output, they put a negative to guarantee that positive output. By putting in like -3, for example, of course it's -1, but the extra negative counteracts it, guaranteeing to get the same output as the absolute value.
Wait, sorry, can you say that again? Sorry, if it's.
So in order to guarantee the same output as an absolute value,
Yeah,
when the input's negative, you got to put another negative to counteract it.
I see.
That's what you have to do. Now if I do my limit as x approaches hold on a sec. Let's clean it up a little bit. Oh, now I'm a little. No, I'm just trying to clean up the expression here. You could try doing this.
Oh. That really don't.
Actually, I'm not sure if that would help us.
Same thing.
How does the piecewise thing?
That won't help us.
I don't-
Yeah, I don't know. I'm not 100%. Well, here's.
This isn't-
Well, hold on a sec. It's actually here's what's happening. Let me show you the left-hand limit. You have to do it more by inspection. Now I'm realizing what's going on here. Both. And I'll do the right-hand limit first. Because first expression I see. Okay. If x is approaching -2 from the right side, this expression is getting positive, right? Positive infinity. So essentially you have positive infinity plus 4. Would you agree with that?
Isn't that just positive?
Right, which is just positive infinity. If I plug a -2 into the bottom one, or close enough, like say -2.001, whatever, same thing, right?
If you plug in what?
Positive infinity?
Yeah, positive infinity is the thing.
No, sorry. What? Sorry. No, plug-in value is close to -2 from the left side,
Oh,
like -2.01, right? So in this case, the limit's going to be positive infinity, or you could say it does not exist.
So how did making it a piecewise function make it easier?
Just to kind of, not really, actually. Yeah. Let's just move on. Yeah, I don't like this problem, actually. I don't really like it anymore. No, 7's a good one, though. Let's do 7. 7's a good one. Yeah, because this will involve limits as x approaches positive negative infinity. All right, let's move on to this one here. To rewrite it, you can rewrite it like this. Okay, let me finish writing. I'll explain what I'm doing. I know, it looks like I'm doing some random stuff.
How do you know that it's -6?
Oh,
Like, how do you
because
find
The
it?
inside, the inside. What makes the inside 0?
Well, yeah, you could have put a lot of stuff. Oh, yeah, that was a huge difference.
Okay, let's talk. So you should recognize that x plus 12x plus 36 is a perfect square trinomial. So x plus 6 raised to the second power. Hopefully you guys can see that. Now, the part that may not be obvious, when you start with the square, it actually leads to an absolute value. So if you square roots the x squared, some people think it's x, that's not true. Has to be this. Very important. The square root of x squared is actually outside of x. So what if I plug in 4? I get 4, right? Because both I plug in -4. The square root of -4 makes it positive 16. Square root of 16 is still positive 4. And remember, square roots, you don't put plus or minus. What's the output for square roots?
Positive.
Only positive, that way they're a function that passes the vertical line test. So you have to guarantee a positive outcome when you square root a square. That's why it's outside of x plus 6. And this gets broken apart into piecewise, like this and this. So assume that you plug in values that are positive here. So this is how I got -6. As I deliberately set this greater than 0 or greater than 0, I solve for x. So anything larger than -6 guarantees that this stays positive. Now the equal sign could have gone to either one. That doesn't matter. I could have put it in first or second. Doesn't matter.
So since if you plug in like the number like -7, for example, that
Right.
doesn't work.
But then I have to use this one instead. To guarantee
-7 plus 6.
is -1, but to make it positive, I have to have that be negative right there.
Yeah, but then the other x will still make it negative, right?
That doesn't matter. It's all about the.
Oh, it's just all, oh, right.
That doesn't matter.
Okay.
So now that's the function I'm looking at. Okay, let me erase the board. Okay, so now for part B, if I take one of those x approaches infinity, am I using the top expression or bottom expression?
But
That's how piecewise helps you. I know I have to use this one if x approaching positive infinity. So basically I'm going to 2 times infinity plus 6.
How often are you compared?
It's just infinity. But for this one, I have to use the bottom one. That's just gonna be -6.
oh, I see. Oh, I see why it's helpful.
Yeah, that's why it's helpful, because if I plug in negative infinity or negative numbers, it's kind of hard to tell what's happening. Because the equation looks so complex from the beginning. Like we don't really deal with like a monomial like x plus a radical of a quadratic. That looks pretty crazy, right? But if I am thoughtful about this, that quadratic is a perfect square trinomial. Oh, if I'm squaring a square, they knock each other out, but leave behind absolute value. Oh, okay, I can absolutize piecewise. Okay, now I got these linear expressions. Okay, now I can handle this. If I'm approaching infinity, I'm using the top expression. If I'm approaching negative, I'm using the bottom expression. Bottom expression, who cares? -6. It's constant. The top one, of course, is linear. That just keeps going up forever as x approaches infinity. So of course I'll say infinity for B. So
What I'm gonna move like
Mhm.
two like what if you had like 2 infinity minus 6 infinity? What would be
Wait, sorry, second.
It's like 2 infinity minus 4 infinity.
That's probably most likely be 0, I think. We'll explore. No, there's problems like that. We'll see. We're not there
Really?
yet. Yeah, we will explore that. Yeah, I have to kind of think about that one because I'm a
It
little
seems
rusty
like
at that.
it'd be 0, 'cause like 2 times infinity is still infinity. And
It's all
4
about what terms are more done. Like if you have e to the x, yeah, if you have e to the x minus x squared, and you
Okay.
plug in infinity, it's actually gonna be infinity, not 0. Because e rises faster than x squared. I know these are things that we have.
Oh, it's like, 'cause it's raised to the infinity versus.
Yeah, and there's something called L'Hopital's. I talk about L'Hopital's rule. That's gonna come back too.
Oh yeah, we could have used that in the homework if we knew how to.
We could, yes, we could have, yeah. Okay, continuity, guys. Let's talk about this. All right. So for continuity, we're just gonna determine whether it's continuous or not, and then name. So this should be pretty fast. So this is yes, this is continuous. This is no, and we'll call that a removable.
We need to know these names.
Oh yeah, that's no.
What is what?
Discontinuity. That's a jump. Discontinuity. Then the last one.
Yeah, it's called.
No. I just can't see because I haven't moved the screen. I don't want to move the screen yet. Oh, thanks.
Stay standing. Let's go.
Was that? And then this one will be infinite, so that's no. And that's also no. That's oscillating.
What is oscillating mean?
Just goes back and forth like crazy. Okay, now let's talk about the rules of continuity, which I think kind of talked about last semester. And then actually, do you do IVT this semester?
Yeah.
In January, we did in January. Okay.
If it's continuous and it crosses 2.
Right. Okay.
Oh wait, yeah.
Okay, but here's a more formal definition of it. F of C exists. The limit. Oh, which one do you need? Sorry. Infinite discontinuity.
Oh yeah.
In order for the second one to be true, the LHL must equal the RHL. And when defining continuity at left or right endpoint, we use the same 3 conditions above, but instead use the appropriate one-side limit for conditions 2 and 3, obviously.
Sorry, can you repeat how's the difference?
1 is the limit exists. 3, 1 and 2 both equal each other. F of C equals the limit.
It's like a Y value for the.
Right, there has to be a Y value, there has to be a limit, and the Y value equals the limit itself, right? Which obviously we've dealt with the whole time. We've known this, but like when you have a jump discontinuity, sorry, a removable discontinuity,
A removable.
like this here, where a point's removed,
Okay.
or you could call it point. So if you look at this one here, right? Clearly F of C exists. Clearly the limit exists. Does F of C equal the limit? No. This fails condition 3.
And so meaning what? It's not continuous.
It's not continuous at X equals C.
Oh.
What if I had this here? Okay, is there a point at X equals C? Sure. But does the limit exist as X approaches C? No. So condition 2 fails, we stop. We don't. I mean, we don't even waste our time checking at 3 because it's not even worth our while, right? Because There's no limit to begin with. So this fails condition 2. So jump to so that's another reason why that would fail, right?
And the first one would just be like, it doesn't even.
Yeah, if you don't have a
Stop.
point there, forget about it. Yeah, then it doesn't even happen. So not necessarily, because look at the removal of this continuity. The limit existed, but FC didn't equal it. Right. Or if you're considering
For the top one? Oh, sorry.
No.
It's removable.
okay, so let's apply this to example 9. All right. So we're gonna rewrite like this. Well, actually, there's no rewrite. Sorry. Where's the start, guys? Okay. If I plug in -4, I should get 2. Plug in -1, I should get 3. Plug in 4, I should get 4. I think I'm doing it right. Yeah. Okay. What's my domain here? Okay.
Well, on the whole time, it's the distance.
For the function. Okay, part B. Yes. And when you prove it,
I need to do all 3.
you gotta say this. Or actually, just say what it is. Right. Why is he doing that? What is that?
I have a suspicion it's for an
Okay. When you do this, I'm asking for continuity. I need to see these 3 things. We got to know this, we got to know this, we get to know this. I need to know each of those 3 things. I mean, it's pretty obvious. Just look at the graph, look at the equation. The limit, of course, equals net 3, and of course, equal each other. I know it seems redundant, but it's what we do. So for C, we'll say yes again. Sorry, no, that's a no. Take it back, it's a no.
You have to show your work more than that, or can you just say that?
That's good enough. So f of -5 equals 1, but the limit as x approaches -5 yeah, that's the reason why. So that's fine too. Sure. Sure. Right, because how can you approach -5 from the left side?
You can't.
Yeah, it's not part of the domain. Yeah. Yeah, and I'll put a little extra note. Can't approach.
You say like -5, superscript, like negative.
Due to domain restriction. Okay. For D, find points of discontinuity. I mean, anything less, that's kind of a weird question. I'd
I don't
say,
think there are point of discontinuity.
yeah, it's kind of a weird one, but
Maybe like
yeah, exactly. That's what I'd say.
a line.
Anything where x is less than -5. But as a continuous function, I'd say yes on its domain. Yeah. So kind of I know because most functions are continuous on their domains unless you do a weird piecewise function. Like, I mean, um, but that's how we would handle that. I mean, yes, the function itself is considered continuous on its domain. If you look down below, it says a function is continuous on in an interval, if only if it's continuous at every point in that interval. But for a function itself to be continuous, it's continuous if it's continuous at every point in its domain. Let me give you an example where that would not happen. Like naturally, the function has a bunch of discontinuities within its domain. You'll see that in just a moment. But in this case, yeah, part E, you'd say yes. Part D, just anything less than -5. But is -5 part of the domain? No. Hence, that's why E is a yes. So that's what's happening with that one.
Why don't you just say yes for you?
It's fine, but I just want to explain to you why.
Yeah.
Okay, can I move forward? All right, let's move to the last page. All right, so 1 over x. What's happening on this one? First of all, is it continuous on this interval? Right, because you have an infinite discontinuity. At x equals 0. What's the domain of this function really? Not all real. Yeah, infinity 0 and 0, infinity 0 not inclusive. Is f a continuous function? The answer is yes. Because it's continuous on its domain.
Didn't we just say that was called an infinite? Oh, no, right.
Right.
So there's a difference because it's continuous. But like, wouldn't this infinite discontinuity continue continues on its domain?
Which one, sorry?
Sorry.
Well, I know what the domain is for that one. But is that the homework or?
This is the one we just did earlier.
Oh, no, it was asking at C. It was asking at C. At x equals C.
Oh.
That's what the question was asking, right?
Oh, yeah.
Didn't it ask that?
I didn't read it, but
Yeah, of course you didn't read it.
well, it's A
And
to
let's
B.
get our time.
So yeah, C is in.
Yeah, yeah, on A to B, right. On A to B, the interval is not, right. Okay. Is
Like,
so now hold on, guys. So this is called the greatest integer function. Not sure if you guys have seen that before. Are you guys familiar with this function? You did? Okay, okay, cool. All right.
Yeah. Oh yeah.
So in case you guys forgot, this is defined as the output is the oh geez, that's hard to read. Yeah, the output is the greatest integer less than the input. What does that mean? So if I were to let's look at like 1.9. If x is 1.99, what's the greatest integer less than 1.99? 1, exactly. So you try to find the greatest integer that's less than that input. Now, once I get to 2, then all of a sudden this jumps. Where does it jump to?
Three.
The next segment. And now you're on this segment, right? So what's the greatest integer? Sorry, it says greatest is less than or equal. Let's say as well. Or equal to the input. So once you get 2, then it's 2. And then it stays that way until you get to 2.9999999, whatever, and then it just keeps jumping. Sometimes we call this a step function because it looks like steps of a staircase. So the domain is not continuous. Clear it's not continuous on its from negative to infinity. So the answer is no. What's the domain here? It is negative infinity to infinity. So is this a continuous function on its domain? No. Because what was that? You could call it that, sure. There's a bunch of jumps. No, because it's discontinuous at each integer. Yeah, that's why. So yeah, that's what's happening there. And I think anyway, one more. Okay, and then we're all done. So let's just give you an example of how you would not be continuous on your domain, because the domain is all real, and clearly it's naturally not continuous on its domain. Whereas 1 over x or radicals, whatever, they're continuous on their domains. All right, last one, example 12. Without sketching, determine analytically. Okay, so let's do the left-hand limit. Let's do the right-hand limit, and let's compare. Left-hand limit. So formally write like this. Limit as x approaches 1 from the left side. Which is really just saying this, right? That's a 2. No, I crossed my Z's because my messy handwriting. It's all good. So the answer is yes. Well, first off, what I really should have done was this. What's f of 1, guys?
2.
And what's my limit as x approaches 1? 2. That's because of all this work I did over here. And then lastly, so these all check out. So the answer is yes. Okay. All right. Well, at least I feel like I closed the loop on that, but I'm not going to start a new topic. I'm not going to give you guys any homework for the weekend. You guys just enjoy it. Okay. And we just hang out, relax for the next 20 minutes. Even though I'd love to let you guys go.
Mark, that's cellular device. Like Arabs.
Like the geography game again?
This is a beautiful place. This feels like
He's going to the sun. Like,
You should say that. You can say, look at the person. He doesn't say about the person.
The clothes. Actually, if I check, it's quite cold there. Right?
What a guess. What the hell? This is that park over by
oh,
for sure.
Well, this is JP's bad.
I think European.
I'd say East. Wait, is it Muslim people? Oh, I would say Morocco.
Morocco.
Oh, not a good look,
It's in
man.
Morocco.
Guess who had a one?
There's 0.0.
Not a good look.
Tunisia.
North Korea, man.
You think this is Africa? Awfully light. These look like guys that Middle East.
Yeah.
That's true.
We're going to use the Middle East. You want to see Lebanon? See Lebanon. Lebanon. Lebanon.
It looked like
Turkey.
Okay. All right.
You've gotten better.
I know. Here, so this one here.
Ferris wheel in the background.
Okay, probably.
Isn't that cool?
I got it.
These people look China.
I'm say China. Yeah, they're all. Oh, yeah.
Whoa.
Oh, this is.
36.
This is
It's
crazy. It's like a movie.
Yeah. That's like
Wow.
Bobby
Gongshi.
Maroney,
So good.
Best 3-point shooters on it.
What the?
This looks like the exact same. This go to six exact same.
And then, how many attempts?
In a ball. Oh my God, how did they get down here?
5 field goals.
What's the person?
Turnovers.
There are people.
Yep.
Man.
Those turnovers, don't worry about it.
How did they get here?
I don't know.
Yeah, I feel like this is how.
Who's the 66? Oh, he's 0.
So
He's
true.
0. No, he's not. Wait, I'm the high.
Sorry, guys, I told you to this.
That's a very diverse geography.
There was like one homework overdue. After the test, is that just like?
You can turn it, it's fine. I'll give,
I already took it. Like,
okay,
review.
I'll take a look at
Alright,
it.
thank you.
It's fine.